Welcome to this class on skeletal muscles part 3 are called as muscle force production and various kinds of muscle force production as part of the Neuroscience of Human Movement course. So, what we will be looking at in this class? We will be looking at types of muscle contraction, we will be talking about isometric force production or isometric contraction, isotonic, eccentric or what are called as lengthening contractions and concentric contractions or what are called as shortening contractions. They are related to each other. Types of muscles, fusiform muscles, parallel fibered muscles and pinnate muscles are different. Actually pinnate muscle has 2-3 types depending upon classification: unipinnate, bipinnate, or if there is more than one angle sometimes it is also called as multipinnate, or bipinnate can also be sometimes called as multipinnate depending on the type of classification. And how is force transmitted? So, force can be transmitted through a tendon to a bone. So, in that case we call it as myotendinous force transmission, or it can be transmitted to neighboring fascial tissue and then to aponeurosis, and then from aponeurosis to the tendon in an indirect way, then we call it as myofascial force transmission. And how to produce quick fast actions and how an electromyography recorded for quick fast actions will look like. So, that is the triphasic EMG part. Okay. So, there are several things that are of interest for us, muscle force and muscle length, right, and we already have seen the relationship, at least in brief we have described the relationship between muscle length and muscle force. An important criterion is the following. So, let me remind you of this criterion that was mentioned. If the muscle tendon unit length remains a constant, iso means equal, metric means length, is it not? So, which length is going to continue to be equal? That is the question. In this case it is not the muscle length, but rather the muscle tendon unit length. This is what we mentioned. Let us look at this in some greater detail. Let us remember the points, the following points, that the muscle is the force producing element in the muscle tendon unit, and the tendon just transmits the force from the muscle to the bone. Movement happens when the bone moves relative to another bone, that is what we see as movement. Now, if you consider a case where the muscle is shortening, so in this case, so now that is the tendon length and that is the muscle length, for example initially, and let us say that the joint angle is some theta. Now, the person is asked to increase the force produced by the muscle without changing theta. Now, what will happen is that theta will remain theta, whereas t will become a new t, which I am going to call that as T1, and m will become m1. Let us remember that m is greater than m1, is it not, whereas t is lesser than T1, or in other words what is going on is that the tendon is contractile, is made of contractile proteins, it is mainly made of collagen. When the muscle is pulling on it, the tendon is going to get pulled and is going to elongate. Actually, depending on the muscle, depending on the particular tendon, the amount of elongation can be relatively large, very large amount of elongation the tendons can take without suffering physical damage, without suffering material damage. They can take relatively large strains. This is an important property of tendons. This is the reason why we do not get injured, although we perform many impact exercises, and many of the impact related injuries are also related to tendon injuries. So, basically if the tendon gets torn, if you overload that, if the tendon gets torn, then that results in some sort of injury. So, the tendon can get pulled much longer. So, T1 becomes greater and M1 becomes smaller than the earlier case. In that case, what will happen is that the force will increase, force increases in this case, but what happens to theta itself? Theta remains a constant between the two cases. So, this is the key, that the joint angle does not change, there is no movement that is produced, movement is not there, yet force is changing. This is the case of isometric contraction or isometric force production, the case in which the this change happens in such a way that m plus t is equal to m1 plus t1. This is the key, this is the isometric part there, or in other words that length remains the same. That length I am going to call as L for example. So, that L remains the same, that is the isometric part. So, in this case m plus t equal to m1 plus t1 is still a problem that I cannot solve uniquely, because there are a number of variables, there are a number of combinations of m1s and t1s that could still satisfy this. This is not, there could be different m1s and t1s that will still sum to m plus t. So, there will be, so I could change this length at different levels, or so that means the force can also be changed over the range of m1. Let us remember that the force length relationship in the muscle is related to not the muscle plus tendon unit length, but rather just the muscle length. M1 alone defines force length relationship, not M1 plus T1. Because of this reason, as M1 changes as a combination of M1 plus T1 being kept constant, force will change. So, I could keep changing the force without changing the length. So, isometric contraction, but it is usually in some cases non-technical people who do not come from the background may say that at constant muscle length force is changed. This is not true. People who are students of this course must be able to distinguish the difference between constant muscle length and constant muscle plus tendon unit length. In this case what remains constant is not the muscle length, it is not m. In particular, important to note that m1 is not equal to m, this is not true, okay. M1 is not equal to m, or M1 this inequality is true, M1 is not equal to m is always true in the isometric force production case. This is critical, it is important to realize this. So, you should never make the mistake of saying that when you say isometric force production, you should never make the mistake of saying that the muscle length remains a constant. What remains constant is the muscle plus tendon unit length. So, these are the trick questions that you get in examinations. So, when people ask like what is isometric force production, immediately we should be in a position to say that the muscle plus tendon unit length remains a constant without change in theta, without change in the joint angle, without change in without any movement that is being produced. Of course, when there is movement, what will happen, that is the question. If theta becomes something, say if theta becomes theta 1 which is less than theta, then that means I am fluxing this arm. Now, that means I am bringing the two bones closer to each other. In that case what happens, that means not only the muscle length changes, actually the everything changes, is it not? Actually theta changes, then there is movement. This case is no longer true. A case in which I am changing the theta, but I am keeping the force produced by a muscle constant. So, in other words, so the force produced can also be called as tension or tone in the muscle. It is a misnomer. So, sometimes people wrongly refer this as tone refers to some amount of tension in the muscle. So, this traditionally this terminology continues in this field. This is the reason why we call an equal force contractions as isotonic contractions, a case in which muscle length changes. So, in this case the muscle plus tendon unit length changes, but the tension or the force produced by the muscle remains approximately the same. So, in that case the contraction is called as isotonic contraction. So, in that case what will happen is that so when would you do that? So, suppose I am having a dumbbell and let us assume that this is a dumbbell and I am performing relatively steady force production with that. I am not doing too fast. Well, in that case the force will quickly change and then drop, but relatively steady curls, bicep curls, right. In such cases the force will remain approximately a constant, it is not exactly a constant, approximately a constant, and that in that case remember that theta was this much here, now that is theta 1, and let us note, and that is theta and that is theta 2, is it not. In that case theta 1 is less than theta, and in this case theta 2 is greater than theta. So, I could do either, right, I could keep it at an angle, I could extend, or I could keep it at an angle and flex. When the muscle is shortening and it is producing a force like in this case. So, in this case what happens is that the muscle is shortening, its length is reducing, is it not. Earlier it was some length L, now it is L1, where L1 is less than L, right. So, in that case the muscle is shortening and is producing a force. A case in which muscle length is shortening is called as concentric contraction or shortening contraction of the muscle. A case in which the muscle length increases, but the force is being produced, right. In this case muscle elongates, like in this case where the muscle length was earlier L and this is some L2. Now, in this case let us remember that L2 is greater than L, is it not. Now, in this case the length increases, and that kind of contractions in which the muscle length increases is called as eccentric contractions or lengthening contractions. Okay. Now, let us remind ourselves of the case of how the force is getting transmitted to the bone and what is the structure of the skeletal muscle. Let us look at the case. So, until this point you have what is called as muscle. So, the whole thing is called as muscle, and this part is called as tendon. Now, what is the fundamental difference? The difference is that the tendon just transmits the force and it is not neurally innervated. The muscle produces and transmits force and is neurally innervated, right. How is this controlled? We have seen. So, within the muscle there are several bundles, primary bundle, secondary bundle, tertiary bundle, etc., and within the smallest bundles there are fascicles that contain arrangements of muscle fibers, and within the fascicle there are several muscle fibers. An important point to note is that the fibers within the fascicle are parallel to each other, but the fascicles themselves are not parallel to each other. So, at the higher level of hierarchy there could be no parallel arrangement, but within the fascicle all the fibers are parallel to each other. In the previous classes what we have seen is that the force produced in a sarcomere gets transmitted serially within the myofibril, there is a serial addition of force, and across fibers there is parallel addition of force, and there is also going to be parallel addition of force across fascicles, across bundles, and so on and so forth, depending on how much the muscle is activated. Now, if some force is produced by this muscle, it is going to be transmitted to the bone. So, this is the bone, to the bone via this tendon. Now, this is a simple case in which the muscle converges into the tendon that is attaching to the bone. In this kind of tendons are also called as external tendons. Okay, the case where the tendon attaches to the bone, they are called as external tendons, but there may be other cases. What are the other cases? Let us take a look at those. In a particular case, several fibers. So, here each inclined fiber, each inclined line represents a fiber, and they all attach to a tendon, and this tendon goes on to attach to a, say, a bone here, for example. Now, note importantly that the thickness of this tendon increases as you come down, is it not? As you come down, you note that the thickness of the tendon increases. This tendon that collects force from multiple fibers and passes on to the external tendon, this part is called as the external tendon. This part where the force from multiple fibers are summed to transmit to the external tendon is called as the internal tendon, also called as aponeurosis, technical term. Force produced by fibers is along their line of action. So, individual fibers pull in that direction, is it not? So, that is the direction of force, but the muscle force is in that direction, is it not? So, what does this mean? This means that not all the force that is produced by the fiber is going to get converted into muscle force. Muscle force is what is felt at the tendon, at the bone tendon junction, whatever is the force that is felt. The muscle line of action of force is in that direction, whereas the muscle fiber line of action of force is in that direction, is it not? So, that means only a component of the fiber produced force gets transmitted to the bone, and obviously that would change as a function of that, is it not, as a function of theta, as theta. Suppose for example, if theta equal to 90 degrees, if theta is 90 degrees, none of the force will get transmitted to the bone, is it not. So, what is preferable in this case is to have theta very small, is it not. So, what would that ideal case be when theta equal to 0 degrees, is it not. So, or in other words, when I have fibers parallel to the tendon. So, suppose that is the tendon and fibers are all parallel to the tendon. So, suppose that is the tendon and that is the muscle, and let us say that is the bone. In this case, you see theta equal to 0 degrees and all the fiber forces gets converted into muscle force. What is the difference between fiber force and muscle force? Fiber force is that force that is produced by individual muscle fibers. Muscle force is the force exerted or force felt by the bone, right. So, this case, this special case has a special name. This is called as, this is actually the parallel fibered muscle. This is the case where all the fibers are parallel to each other and attached to the tendon directly. So, in that case all the fiber force will get transmitted faithfully. This is a relatively rare case. This is more prevalent. Why? Why would evolution prefer this model? Why? Because I could pack more number of fibers in such arrangements, in such complex geometries. I could pack many more fibers than I would be able to do that if I were to pack the same number of fibers, assuming that all individual fibers produce the same amount of force. If I would like to pack more fibers, I will require greater amount of volume to pack this, is it not? This volume I cannot afford, because body size can only be so much. I cannot keep increasing the body size indefinitely. Because of limitations, because of constraints in the body size, it turns out that I am interested in coming up with more complex architectures, more complex geometries, more complex morphologies, in which I am able to compromise. I am able to find a trade off between morphology, between the structure and the amount of force transmitted. Obviously, this arrangement is less efficient. Anyone with basic physics knowledge will be able to say that, well, that is a very poor arrangement, because as I am producing more force, but not all the force gets transmitted. In other words, I am exerting more energy than what is actually getting used, very poor arrangement. But evolutionarily, biological system need not work necessarily from an engineering perspective. What this is trying to do is, I am trying to pack more volume, and I am trying to, why would we need more volume? Because the total force that is needed would be greater. Total force that can be produced by a pennate muscle would be greater. And there are other arrangements. For example, this arrangement of a bipennate muscle where there are two angles in which this is attaching. Again, note importantly that as the internal tendon goes on to attach to the external tendon, or as the aponeurosis goes on to attach to the external tendon, look at how the aponeurosis becomes thicker as you go down. So, if you are going down, you can note that the aponeurosis is becoming slightly thicker with each. Okay. There are more complex morphologies not discussed. The other case is the case of spindle shaped muscle or the fusiform muscle. In this case what happens, or this is the usual muscle example that is given by many people. So, in this case what happens is that there are fibers whose length is equal to the muscle length, and then there are fibers whose length is greater than the muscle length. So, because this forms a slight arc, if I take this, I am going to draw this with a different color just for clarity, right. If I take that blue line and straighten it, and I am going to find a length L1, and if I take the red line which is in the middle and straighten it, I am going to find L. Anybody can say from intuition that L1 will be greater than L. So, in this case, and there are several L's along the way. So, as you move from the center of the muscle to the periphery of the muscle, the length of the individual fibers keeps changing, and in this case again not all the force that is going to be transmitted to the bone, but it is not just that, there is more complexity involved in this case also. What also happens is some fibers start from here and end there, and then there are other fibers that start from here and end there. There are fibers that start from one end to the from one end and end at the other end. This kind of fibers are called as spanning fibers. These span the entire length of the muscle, so they are called as spanning fibers. And then the case where some fibers start at one end, but end in the middle of the muscle, do not continue till the end of the muscle, the other end it does not go. For example, these two cases, right. A question is how can force be transmitted in such a case? Because if this fiber is getting activated by the neuron, then the sarcomeres in that are going to contract due to excitation contraction coupling, and some force is going to get produced. Then this force is going to be useful only if it is going to get transmitted to that point, right. Is that, how is that achieved is a question. This is still the subject of intense research. What is known at least is the following, that there is parallel force transmission, some amount of force gets transmitted in these directions, not all. So, this kind of force transmission that happens from fibers to neighboring fascial tissues is called as myofascial. So, this type of fibers that end in the middle are called as non-spanning fibers. Okay. And this type of force that gets transmitted from fibers to neighboring fascial tissues are called as myofascial force transmissions. As you age, what would happen to the pennation angle would be a question. Suppose why is that even important? Because you see pennation is present in all people, in all muscles, in many muscles, right. So, there is this feature that is present everywhere, but the angle could change as a function of age, exercise, etc. How does that change? Pennation, for example, would increase or decrease depending on these features. What would happen with age? Right? What would happen is usually what is desirable? What is desirable is to have the pennation angle relatively small, closer to parallel fiber. Is it not? That is the aim, because we want to get maximum force that is transmitted. That is going to happen when theta is close to 0, or when it is closer to the aponeurosis angle. So, that happens with age, but that happens due to a different problem, right. That happens because many fibers die out or become orphaned, and because of that reason these become straightened, these become closer to the aponeurosis with age. When you lift weights, perform strength training, let us say you are a bodybuilder, you are trying to perform exercise, what you are doing is you are adding more and more fibers, you are adding more volume, you are adding more bulk to the muscle. You cannot do that indefinitely because of space constraints. So, what will then happen in such cases is that the pennation angle will become greater as you are exercising, pennation angle will become greater. Note, that means is aging good or not exercising good? No, there are multiple things, it is not just penetration angle, the total amount of force that is produced reduces because of the number of fibers. So, there are two things, one is theta, as theta increases, force contribution or the component of force that is getting transmitted reduces, and as the number of fibers increases, force increases. But it turns out that the number of fibers that increase due to exercise is much greater than the reduction in force due to increase in theta, which is why if you exercise you are able to lift heavier weights as you go along, right, but it does cause a reduction in force or an increase in theta. Okay. There is more details, this I have just covered the basics of this topic, there is more detail, those who are interested can verify, can check biomechanics of skeletal muscles, Zatsorsky. You can check this book and more detail and more morphological structures and the various possibilities are all presented. An important point to note is that from the control viewpoint we are interested in the neuroscience of movement more than the morphology of muscles. This is structure related, but we are more interested in control, right. From the control viewpoint it is important to note that I do not know the theta, I do not know the change in theta, I do not know what component is myofascial, I do not know many things with respect to muscle force. So, it is very difficult for the system to specify forces, it would not be possible for the system to know so many fibers I will need to recruit, and if I recruit so many fibers exactly so many millinewton of forces or so many newtons or whatever, so many kilonewtons of force will be produced. That is something that is going to be very difficult for the system or a controller, if there is a controller, to predict. Why? Because I do not know the thetas. By the way, it is also possible that the thetas will vary as a function of the fibers. We have only shown some cases. Between fibers there could be variability. Theta is actually, I have the picture is drawn in such a way that theta is the same across these, but here is at least a more complicated case where there are two thetas, but there can be multiple thetas in multi-pennate case. So, I do not know. In the fusiform case I do not know what proportion of the fibers are actually non-spanning and what proportion of the non-spanning fiber force is going to get transmitted through the myofascial transmission. So, without knowing all those things it is very difficult for me to recruit fibers in such a way to ensure that I get a specific amount of force, yet humans are able to perform very dexterous and well controlled movements. It remains a mystery how they are doing it. That is the purpose of this course, to clarify that mystery to some extent. Also we have discussed this, fascicle arrangements vary considerably, because I mentioned this earlier that within the fascicle fibers are all parallel to each other, but fascicles need not be parallel, can result in very complicated architecture. So, muscles with very different shapes, very different functional capabilities are there. A particular case is the case of the convergent muscles. Example is the chest muscle or the pectoralis muscle, shortly called as the pec muscle, right. This muscle is a convergent muscle, or what is called as a triangular muscle. In that case one part of the muscle is broad whereas the other part of the muscle is thin. So, this length is different from this length. See the chest muscle, this is the architecture, the fibers are running like this, alright. So, these type of muscles are called as convergent muscles. More complicated structures are available, circular muscles that are found in the mouth, an important and well controlled muscle. So, if I am speaking out specific alphabets, that is due to the amount of orifice, the size of the orifice varies, and as the air moves out specific alphabets or specific words or phonemes are spoken out. Very well controlled, precisely controlled muscle. How does the geometry affect in these cases? So, several of these are present and we have seen these cases, fusiform, parallel and pennate, which are the most common or the more common cases. And as I said, when force gets transmitted from a fiber to a tendon, that is straightforward myotendinous force transmission. When force transmitted is from one fiber to an aponeurosis, from an aponeurosis to a tendon. This is basically myofascial force transmission. Let us remember that we do not know what proportion of force gets transmitted. We may not be able to exactly estimate theta. From this picture, if I am giving you this picture and ask you to estimate theta, then it is possible for me. It is for me to estimate, and if I am telling the force produced by each fiber, then it is possible for you to estimate what is the force that is going to, that is going to be achieved at that point, that anyone with basic physics and engineering mechanics knowledge can do. But from a controller viewpoint, it is not reasonable for me to expect that the system, that the controller somehow knows what the theta is or the thetas are. There may be multiple thetas, and only if I know all the thetas, I am going to be able to know what is the force produced by that muscle or which fibers to recruit. So, it is a relatively more complicated problem than what appears, and even more complicated is this case, how much of this transmission is happening in parallel. So, control cannot be so precise, control cannot be the control in the engineering sense. Another case is the case of how displacement is produced, or smooth displacement is produced in relatively fast actions. Suppose I am making a fast reaching action, suppose I am doing that, right. Important to note is that the key word here is fast. In fast actions, I am interested in two things. I am interested in reaching to a particular destination. So, what is shown here is the trajectory. So, that is the trajectory, and what is shown on these with the dark lines is the is one is the agonist burst, and the light lines is another type of activity. So, if I am producing a fast action, usually there is co-activation of both the agonist and the antagonist. We define what is an agonist and what is an antagonist. For a particular action, one muscle can be agonist, and the muscle on the other side that prevents, that deters movement of this that deters this movement can be considered antagonist. For example, in this case we are considering, say, elbow flexion or elbow extension, as the case may be. Suppose for elbow flexion, biceps can be considered as the agonist and triceps is the antagonist. So, triceps opposes flexion, it tries to prevent flexion. Simultaneously both of these are co-activated. Why are these co-activated remains a $1,000,000 question. Why do we have to do this? I could individually control one muscle and present relatively accurate control signals to one individual muscle and then get the same output. Is that even possible? From an engineering viewpoint that might make sense, but however in the biological system this is hard to achieve. So, I am interested in producing a fast action, right. So, in that case I have to control the velocity. If I allow one muscle to supersede the other muscle, then what will happen is that I may miss the target, and this has consequences, important consequences. Suppose I want to catch that cup, for example, right. If I overshoot, it is entirely possible that I could drop this cup. So, such actions are not desirable. So, you want to stop at a particular point, right. And if it is a fast action that you are interested in performing, let us say you want to quickly pick up a pen, right. In such cases your movement should be controlled to multiple aspects of your movement must be controlled, not just the end point. There are several things. End point, you have to reach the end point, it is critical. You do not want to miss the end point, you do not want to overshoot, you do not want to miss the end point. So, that is important obviously. Trajectory, is trajectory control important? To some extent trajectory control is important. Another thing is velocity. So, several things come into the picture, several parameters that are not immediately obvious come into the picture into control of this. So, the first agonist burst includes sometimes co-activation of the antagonist. After some time, toward the middle of the displacement here, at around not exactly at the middle, approximately in the middle of the antagonist here, there is going to be an antagonist burst like that. This results in slowing down. Why is this important? Because at around this point, if these were the displacement curves, what would my velocity curves look like? So, here the velocity will start increasing and at some point reduce, because why does this reduce? Well, actually ideally this is going to look something like this. This is the velocity curve, not. So, why? Because I have to slow down, because I have to stop here. It is a different target, obviously that this is the net displacement, so many mm's or so many centimeters or whatever. This is the displacement, this is the net displacement that is achieved, but I want to, at this point I want to stop. If I have to stop, then I have to slow down here. So, to slow down, I am activating the opposing muscle while switching off the muscle that is for a brief period, the muscle that is producing the movements, thus effectively slowing down this trajectory, that slows down, and then again there is a second agonist burst that brings this to a stop. So, this case where there are 3 phases, the first agonist burst, the antagonist burst, followed by the second agonist burst, there are 3 phases. This is called as a triphasic EMG pattern. Important to note is that this may not be observable in relatively slow action. So, if the action is relatively slow, it is possible that there will be no antagonist burst, that anybody can guess. If I am making this movement relatively slowly, it may not be necessary for me to slow down, because I am already moving slowly. The moment to moment control may still be sufficient with just one burst. Okay. So, in this class what we have seen is isometric, isotonic, eccentric and concentric contractions and different types of muscle fiber arrangements. So, fusiform, parallel, pinnate, and we have also seen other cases, other special cases like convergent, circular, etc., and what happens with those. At least we have introduced those topics, and how force gets transmitted to a tendon directly. So, it is myotendinous force transmission, and how it gets indirectly transmitted to the tendon, or myofascial force transmission, and we have seen the case of triphasic EMG in fast actions. Okay. So, with this we will end this class. We come to the end of the lecture on skeletal muscles. So, thank you very much.